And we are live. Okay. Welcome to Math with Doug, Geometry with Doug, Surface Area with Doug. We did surface area last week and we had a bunch of shapes that we saw, quite a few actually. But this week I am going to restrict us to fewer shapes, including a new shape, which is the cylinder. And I kind of was thinking about whether this is a good idea, why it's a good idea, and I like it. I like this idea because we want to start facing the idea of lateral area versus total area, which is, they're both surface area. And a lot of the shapes you can end up sometimes needing the lateral area, sometimes needing the total area, but I'll get into it when we look at the cylinders. I think cylinders are a good way to introduce this topic. This is Mocha. She has to wait 1 hour from this moment right now for her supper. And she's going to lie down on her comfy armchair and be well behaved. And I'll think about whether after an hour of that, whether she's been good enough for supper. We all know what's going to happen. She knows what's going to happen. She's grumbling at me right now. She's going, she can tell that I'm having an attitude. This is Harlequins. This is a rugby team from London. Beautiful jersey with one of the coolest logos ever for a sports team. I really like this jersey. Okay, the weather, spring. I'm glad it's spring. But now let's get into the math. Now, if it's surface area, why do I have these two drawings of rectangles with lines across this one and along the side of that one? There is a reason. I think I decided for my cylinders, I wanted to make cylinders to use for the lesson, at least for our first few examples. And I thought I'd like to make cylinders that students could also make. So I started thinking of my strategy for how I would like to make cylinder out of a piece of paper that we could then find the surface area of and find its lateral area. That's only the tube part of the cylinder, and its total area, which is the tube plus the two circles at the ends of the cylinder. When I actually put a cylinder in front of you, we will all understand what I'm talking about. So I used an ordinary 8.5 inch by 11 inch sheet of paper like this one, because I figure any student who's watching probably has access to paper that's already cut to that size, and that means a student can reproduce the same cylinders that I'm about to show you. So I just thought that would be a good idea. Okay, I'm going to start with this cylinder. So this cylinder is obviously made by rolling a piece of paper up, and I taped it. I taped the two ends together so that it would stay in the cylinder form. And you can see what a cylinder is. It's this tube, this rounded curved face, which can be unrolled in a net to form a rectangle, which is kind of convenient. And you can see the circles at each end. The two circles are the same size because a cylinder is a type of prism. A prism, and this is a review, I explained this already, a prism is a shape where the base is the exact same size and shape as the opposite face. And that is sort of the definition of what makes something a prism. So there's all sorts of different types of prism. You can refer to the cylinder as a circular prism if you wish, because that's what it is. So I made one. But to do that, to tape it together in a way that would work, it was easier if I let the edge of the piece of paper overlap a little bit. So I did that, and I did it with a strategy. And we can see the strategy right here. So this rectangle is an 8.5 inch by 11 inch rectangle. But I drew a line separating 1 inch at the end. So the 11 inches now is a 10 inch long side with an extra inch. And that explains how I made this. I made the paper overlap by exactly 1 inch. Why did I do that? Because it's convenient that we're dealing with 8.5, which is a nice easy number to deal with, not too decimally, not too confusing, by 10, and 10 is of course a really easy number to work with. So I'm subtracting 1 inch by overlapping it, and that means that the circumference, so yeah, we're talking about circles because there are circles involved here, and we know all about circumference. We've done the circumference formula for a while now. The circumference of this circle is 10 inches. And that's convenient, easy number to work with. So that was my strategy, and that means any student who wants to can do the same thing, so long as they have a piece of paper this size. So I'm showing 11 minus 1 equals 10 because I'm a math teacher, I'm like that. When I do anything in math, I want to always explain every step of what I'm doing, showing all my steps. So I am showing where I got that 10 inches. I got it by subtracting 1 inch from 11 inches. Now we all know why. What's happening over here? What's happening over here is the fact that I was able to make two different cylinders from two sheets of paper that are the same size. So as you can see, the circle at the ends of this one and my right hand are smaller, which means the circle has a smaller radius and a smaller circumference. But the length of the tube is longer. This makes sense when you realize that you can take the same size sheet of paper and instead of overlapping 1 inch along this shorter side when you tape it together, instead you overlap ½ an inch along this long side when taping it together. This tape, we can see it. This one didn't tape together quite as neatly. I was a little clumsy with it, but it works. We have a cylinder and we can find its lateral area and its total area. So we have two cylinders and we can find both of their lateral areas and total areas. And these diagrams show how I made them. Why did I only overlap ½ an inch here? Because I'm cutting off some from the 8.5 inch side, the 8.5 inch side. So cutting off a half means 8.5 minus a half equals 8. And that 8 is a nice clean number. This one's even cleaner. We have, if we disregard the overlap, because we will, we have 8 inch by 11 inch. Nice easy rectangle. This one almost as easy, 8.5 inch by 10 inch. We are able that quickly to make two different cylinders, which are going to have two different surface areas. Let's think about that. Students are welcome to think about that. This one is longer, but it's skinnier. It might look like it would have a smaller surface area, but wait, they're both made out of the same sheet of paper. Wouldn't both of the 8.5 by 11 inch sheets of paper have the same area, the area of a rectangle? Yes, they would. So are these going to have the same surface area? We're going to find out, aren't we? Okay, I'll put those down. I'm going to take a sip of my fizzy water. It is lemon flavored fizzy water this time. Just explaining what I did with two sheets of paper took almost 8 minutes of the time of our lesson. We can see why I want these video lessons to be 1 hour long. There are good reasons to do that. Trying to do a math lesson in 3 minutes, well, it can be done, and I have done it before, but there's only so much you can achieve with that. If you want to go into a subject with any depth, then give it a bit more time, introduce more examples, think about the problems from different directions, like, oh yeah, I can do this with a sheet of paper, and I can do this very similar but different thing with a sheet of paper, and that's kind of where the learning happens. And I like the idea that the students can do this themselves because it turns this sort of lesson into a math lab. I think math labs are a good idea because labs are always a good idea. When you're in the lab, learning works better because you're really making things actually happen instead of just looking at words on a page and thinking about how things work. You're making things work right in front of your eyes. I like that. Okay, so we're going to start looking at the formulas for surface area of a cylinder. And we're going to start with the lateral area, which is the tube only. That is actually all we have here because I didn't make circular pieces of paper to cover the ends of this. Later on, we'll just imagine that there are circles on the ends. The circles are there, but is there a piece of paper there? So what is the area of this piece of paper? We're about to find out. This is this one. So the area formula, and I can call it A sub L. I like doing things like that, meaning lateral area this time. The lateral area of a cylinder formula is 2 pi, my handwriting is messy because I'm not standing on the side I'm used to, 2 pi r h. Not a very difficult looking formula to use. We need the h, which is the height. That's the length of the tube. So this is something where it's good to slow down a bit because the h it makes sense to call this the height when you have it standing on end like this. The thing is that this is still going to be a cylinder if it's not standing on end. And then you might think, wait, where's that H for height? I'm confused. I would use L for length now. So the length of this tube, which is the height of this tube when I hold it on end like this, it's very light so it wants to fall off, is how long? How long is this H? When we think about how we started, it's going to be 8.5 inches. So I'm going to start filling in the formula right away. Way over here where the H is going to go, I'm going to leave some room for all the 2 pi r stuff. I'm going to put the 8.5. That's my H. But wait, what about the radius? We don't know the radius. I could measure the radius. I could grab a ruler and try to measure across the diameter of this circle and figure out what the radius is. But I want to calculate the radius. Didn't I say before that the circumference of this circle has to be 10 inches? Yes, I did. So I'm going to go over here. Let me move my chair out of the way. And I'm getting out of the way. I'm nearly going off camera, but I want the circumference formula to show. Will this show? Yes. Circumference equals 2 pi r. We know that. That's a review. So that's going to be 2 times 3.14 times r. I don't know the radius, but I do know the circumference. The circumference is 10 inches. So I'm writing 10, move this little smudge, 10 equals 2 pi r, and I'm able to find out the radius by doing the circumference formula kind of backwards. So what I'm going to do is divide both sides by 2 and pi. Cancel, cancel. My r is isolated, and it's equal to 10 divided by 2 divided by pi. So I'll grab my calculator and I'll get that. 10 divided by 2 divided by 3.14. Yes, I will be using 3.14 for pi for this whole lesson. 1.59, that is rounded to the nearest hundredth. It's a decimal that goes on forever, which tends to happen when you involve pi in something. So I'm rounding it to 1.59. But I know these students can handle some decimals. That's not so difficult. Oh, now I know the r is 1.59 in this formula, and that's going to go right here. Okay, that 9's kind of skinny. Hope it looks like a 9. Good enough. Okay, and of course, I'm going to move my equal sign further over so I have room. We have 2, and we're going to use 3.14 as pi. All we have to do is multiply, and we will have found the lateral area of that cylinder, the tube-only area of that first cylinder. And I also just, before I do that, I just want to point out something. 2 pi r, we've seen that before, haven't we? Yes, we saw it right here. So, interestingly, 2 pi r is being used twice, just doing this first lateral area formula. I used 2 pi r to figure out the radius of that circle because I need it in here. And then the formula is just 2 pi r, which is the circumference formula, times the h. That's kind of interesting when you think about how someone figured out this formula would work in the first place. The use of pi and the use of the simpler formulas that go with the circle, like pi r squared and 2 pi r or pi d, keeps on cropping up when we work with other more complicated shapes that involve circles, like the cylinder. I never even wrote the word cylinder. There's a lot of cylinders in today's lesson, so I'm going to write the word cylinder. Okay, I'm getting there. I know I get off to a pretty slow start at the beginning of these lessons, but that's what happens. Okay, using calculator, let's multiply. We will find our lateral area. 2 times 3.14 times 1.59 times 8.5, 84.8742. I'm going to call it 84.9. And that's going to be inches squared. Remember, it's an area. An area has square units. And we were measuring this piece of paper with inches to start with. Our cylinder, we were using inches. So everything up, this r equals 1.59. That I should have written inches, so I'll just stick it in now. Okay, now that's the lateral area. But what if this tube did have the circles at each end? We would then be looking at the total area. Now this is going to happen sometimes, right? You can have a tube where you don't want circles, you don't want to close off the ends, like pipes. that are being used to transport water or other liquids from place to place. So you might need to find the lateral area of that pipe in order to figure out how much cement you have to pour in to make the pipe. But there are also cylinders where you do want to block off the ends, like tin cans. Cylinders are all over the place. All you have to do is go into a pantry, and you might find all sorts of tin cans with different heights and radiuses. They're just different cylinders. And then the tin can itself, the can of food itself, can be extremely useful for illustrating the math of cylinders, because often tin cans have a paper label. A paper label will be shaped kind of like this. The paper label will represent the lateral area, but the metal that was used to make the tin can would represent the total area. And it's just a nice little illustration of the difference between lateral area and total area. You need metal on this curvy side surface, but also on the top and the bottom if you want the can to hold something. And if you want to make the label, the paper label for that can, then you're actually only needing the lateral area. Most tin cans don't have any paper on the top or the bottom. So a good example that's often easily found in any household. Very useful, like this size piece of paper is often found in any household. So I keep on reaching for things that I know other people watching the video could also reach for. It's useful in the math. You get your hands right on it. It's a math lab. Okay, I want to find the total area, and I'm going to call that AT. So A sub T, I'll put a little line here. A sub T has a formula, and it is 2 pi RH plus 2 pi R squared. Okay, let's look at this formula. Does this make sense? It's long. Some people might say, oh, it's too long, I don't want to understand it. But no, we have to understand it. Well, the 2 pi RH thing might have looked weird once upon a time, but not anymore, because that's the lateral area. All we're doing is we're taking the lateral area and we're adding this other thing. The other thing, obviously, is the area of the two circles. And pi r squared, we've seen that before too. So we see 2 pi r, which is circumference that we already knew, and we see pi r squared, which is the area of a circle that we already knew. And we realize, actually, all this new stuff we're learning includes a whole lot of stuff that we already knew, and that's good. We are building upon our prior knowledge. 2 is there because there are 2 circles. There are 2 circles at the ends of the cylinder. So we need the area of a circle twice. It all makes sense. And then filling in this formula becomes faster because of the fact that we already found the lateral area. We already know that 2 pi RH gives 84.9, so I am doing a shortcut and putting 84.9 here. But I'm going to fill in the 2 pi r squared part. 2 is of course, I'm just writing a 2, but pi I'm rewriting as 3.14. The r, it's the same r. It's that 1.59 that we found earlier. So that came in handy more than once. But that r now has to be squared. So 84.9 plus 2 times pi plus times 1.59 squared. Remember the order of operations. That's the first time this has happened with these formulas, because here all we did was multiply, but here we have an exponent. So following the order of operations, we square the 1.59 first. Then we multiply by this other stuff, and the adding, the plus, will be done later. I want to make it all fit, so I'm going to go equals here and keep going. 84.9, try not to write too large, plus 2 times pi times the answer to 1.59 squared, so I'm going to do that now. 1.59, now that's already rounded. I could have used that long decimal and it would be a little more exact, but we did some rounding. 1.59 squared is 2.5281. That's kind of long. I'll put it though. 2.5281. So far I've only rounded once. And then I'll write an equals 84.9. I have to make sure that I'm not going down below the rectangle that the video can see, but it looks like I'll have room. Now I can multiply 2 times 3.14 times 2.5281. 15.876, and it's a decimal. I have to round again. So I'm going to round it to 15.9. And we pause and think about what we've achieved. We have this 84.9 that we've known about for a while. That's the lateral area. But now we know that the total of the areas of those two circles at the ends of that cylinder is 15.9 square inches. We still have to add and get our final answer. 15.9 plus 84.9 gives me 100.8 square inches. It is an area. We have a square unit. Can't believe I've already used 20 minutes and I've just done the first cylinder. Okay, but it is worth going slow when you're introducing something new, and there's a lot of complexity to this issue, this topic. A lot of complexity. The cylinder isn't something that you just look at once and you understand everything. There's a lot to do, so I don't want to go too fast. 100.8 inches squared. We can see that for this cylinder, and I'll show us the cylinder again. Most of the area is the lateral part, the label of the tin can part, the tube part. And only this small chunk is the circles at the end part. But that's because this has a rather long height and not such a long radius. And a cylinder doesn't have to only have a long height and a short radius. Cylinders can have any combination of height and radius, and that's why we need more than one cylinder. Let's look at this one very quickly. This one actually, it's got not a very long height. It's a roll of painter's tape. Not very much in the way of height. The radius is actually longer than the height. So the lateral area of this one, we might have time to do this later. I can predict though, the lateral area of this one, that part that happens, the 2 pi RH part, is going to be smaller than the 2 pi r squared part. You can sort of see that when you see how big an area is this rolled up rectangle that I am showing you, the blue part. Compare that to how big is the area of that circle, and then of course there are 2 of them. So yeah, interesting. In this case, the second number, the 2 pi r squared, will be bigger, but in the case of our original paper cylinder, the first part, the lateral area, the 2 part, ends up being bigger. It's worth it to take your time and spend a lot of time on this shape, a special shape. Now, I've got the 100.8 inches squared, and I've got the 84.9 inches squared, and I also have them written on my chalkboard wall over there where you can't see, because I might want to talk about those again, but first I have to do some erasing, because I want to do this all over again, but for this other one, for this longer, skinnier cylinder made out of the same sheet of paper, because I want us to be able to compare. Will we get the same lateral area for this longer, skinnier one as we just got? Will we get the same total area? Will it be different? We're going to find out. And that means I want to remember these 2 numbers, which is why I wrote them down over there. So time to do some erasing. And I can even erase this diagram. Should I? I think I won't. I'll have enough room to do all of this for that one. So I'm going to leave the diagram and the little circumference formula where we found our radius. And I'm going to erase all of this. Okay, so we're doing it again, but the first thing we have to do is the circumference formula to find the radius of this circle. It's not going to be the same radius. It's obviously going to be smaller. Let's find it. And you have to be careful, because it's easy to get the 2 numbers mixed up and use the wrong one when you're trying to find the circumference. This helps me to remind me to not mix them up. I used the 10 inches for the circumference for this first example, but for this one, because I put this strip on the different side, I'm going to be using the 8. So I'm going to do that circumference formula, and I think I'll be able to fit it right here. Circumference equals 2 pi r. Our circumference, that's a weird r, our circumference is 8. So I'm replacing the c with the first circumference with an 8. I'm replacing pi with 3.14 as usual. And r is what we're going to find. And that means I am going to divide both sides by 2 and by pi. Cancel, 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 cancel. R is isolated. Make sure that still shows. Yes, it does. And is equal to 8 divided by 2 divided by pi. Let's get the calculator. We're going to have to do some rounding. 8 divided by 2 equals 4. No one is surprised about that. But I still have to divide by pi. 1.2738, I'm going to call it 1.27. And this time I'm remembering, I'm putting the little abbreviation for inches. I don't know how well we can see that. That's okay. Okay, so we have a 1.27 inch radius this time. We're ready to go ahead and fill in our lateral area formula again. Area lateral equals 2 pi r h. Will I have trouble remembering this formula? No. It's the circumference formula times the h. Not so hard to remember at all, actually. Equals 2 times 3.14 times this radius, which was 1.27. And here's another moment when we have to slow down and be careful. Wait, the h, is it the 8 or is it the 11? This actually makes it easier to remember that than this drawing. It's the height, that's the length of the tube, and I call it height because I have it balanced on end like this. That's 11 inches. Nothing was cut off of that. So it's 11 inches. I'm putting in 11. Okay, so the formulas have a lot of stuff that's the same and some stuff that's a little different. All I have to do is multiply. Let's get the calculator and multiply this out. 2 times 3.14 times 1.27 times 11 equals 87.7. Again, I'm rounding to the nearest tenth. 87.7 square inches. What was it again? The lateral area of the other first cylinder, this one, it was 84.9, a little smaller. So that means this area is a little smaller, this lateral area, the area of the tube, the area of the paper, is a little smaller than this one. Interesting. We might have predicted it would have to be exactly the same. We have to think about why it's different. Think about that for a minute while I get set up to do the next formula. Area total equals 2 pi r h plus 2 pi r squared. And we're ready to fill this in right away because we have everything we need. Finding that radius has been so useful. You would look at this problem and think, oh wait, I don't know where to start, if you didn't already do the little circumference formula, find the radius. Very useful to know these other little formulas. Okay, so the area total is 2 pi r h, which we know is going to be 87.7. If only I could write an 8. 87.7 plus 2 times pi times r squared. That's 1.27 squared. Which is 87.7 plus, and I'm not multiplying yet, 2 times 3.14 times the answer to 1.27 squared. Remember, this is the point at which we want to be careful to follow the order of operations. 1.27 squared, 1.6129. I'll just write out all of that. It stops there. I'll write all of that. But of course, I had already rounded earlier, which is why I'm not getting a decimal that's going on forever. 1.6129. Now we can multiply. 87.7, can't use that yet. Order of operations, multiply before adding, plus 2, well the 1.6129 is already in my calculator, so I'm saying times 2 times pi. 10.129, I'll say 10.1. It's another thing to stop and notice. Remember the area of the circles at the ends of the first cylinder, the one with bigger circles at the ends, was 15 point something. And this is only 10.1. Well, it makes sense though, doesn't it? Look at the circles. These two circles are obviously smaller in area than these two. So by comparing two formulas where some things are the same, the pieces of paper are the same, and seeing how things differ, we learn. Okay, 87.7 plus 10.1 is going to give me 97.8 square inches. It's an area, its units are squared. So remember the total area of the first cylinder, this fatter, shorter cylinder, was 100.8. The total area of this taller, skinnier cylinder is 97.8. This total area is smaller than this one. But the lateral area of this one was smaller than this. So interesting. Why did that happen? Why did I not just get all the areas the same because they were all made from the same size sheet of paper? We have the answer. I know you've had time to think about it. I know you know the answer. Because when we cut off 1 inch strip of this one, we were cutting off a different amount of area than when we cut off this 1/2 inch strip on this other one. So that slight little difference in strategy for how we folded the paper together to make our cylinder caused these two lateral areas to be different, and it also caused the total areas to be different. And when you really think about it, it makes sense, which is hopefully how you feel, because I know students are learning when they think about stuff like that and have it make sense. These are the what if questions. So what if we take the same standard sheet of paper but remove 2 different sized strips of paper and then form it into a 3-dimensional object like a cylinder, and then find its lateral and the total areas? What will happen? Well, we just saw what will happen. We saw it happen. Now that's 4 formulas, 6 formulas if you want to count these 2 little circumference formulas. So I can call that 6 examples if I want. And I've used half of my time. Whew, that was fast. Okay, I'm going to break away from the cylinder for a very short time to talk about the sphere. Yes, we covered the sphere last week, and we found the surface area of the sphere. And we used an earth ball and we used medicine ball, earth ball, and these exercise balls. I wanted to have different sized spheres, and I just chose those. I don't know, it just seemed fun to choose big ones. Like an earth ball is really big, and medicine ball is pretty big, and those exercise balls, they get pretty big depending on the size of the person who is exercising on them. So this time I'm going to do 2 spheres, only 2, and I'm going to use a basketball, which is one of the standard sizes for a basketball. I went and did a search to see, well, what are the sizes of basketballs and how big are the radiuses? I needed the radius so that I could do the sphere formula. And the other one is going to be a soccer ball. Now, is this a size 4 or size 5? I know a little bit more about the sizes of soccer balls. Unfortunately, it doesn't look like anyone ever printed the size of this one. I think it's a normal size one, I'm not even sure. So it might be a size 4, it might be a size 5, but it doesn't matter. I looked up the radiuses of soccer balls and basketballs, and we're going to talk about the sphere again. We already did that, but what are we doing differently this week? We're now considering the idea of lateral area versus total area, and we see how that is different with the cylinder, but how will it be different with the sphere? Stay, someone's at the door, and she's going to react. I just don't want her to start barking. Lie down, stay. Okay, yes, there is an audience member who's not asleep after all. The good news here is I can erase all of these formulas, including these circumference formulas, but I can also erase these diagrams of the sheets of paper. So I have a lot of room to work with. Will I need a lot of room when I'm talking about the sphere? Well, we're about to find out. So, the basketball I will do first. Basketball, and I'll write sphere here. It's only fair. We covered cylinders, and now we're covering spheres. The basketball. And if to do the surface area of a sphere, we need one thing only, which is the radius. So I'm going to give the radius. The radius of the basketball, well, at least the size that I found when I did my search, which I think matches the basketball I have, is 5 inches. Okay, so what did we learn about surface area of the sphere last year? The surface area formula was area equals 4 pi r squared, and we had looked at that and said, okay, that's interesting, pi r squared, that's the area of a circle. And obviously a circle has something to do with this shape, because, well, if it were flat, it would be a circle. So it has a circumference. It's kind of neat. Sphere has a circumference, it's just that it has a whole bunch of circumferences that go in all directions, whereas your typical circle just has that one circumference. It's the difference between the 2D shape and a 3D shape. Okay, I don't need that. I'm going to erase it. So pi r squared, the area of a circle, times 4 gives the area, but which one? Does it give the lateral area or the total area? Let's stop and think. Well, let me first stop and take a sip of this fizzy water. That was necessary. What's the difference again between lateral area and total area? The lateral area is just the tube, and the total area also includes the circles, these bases, circular bases. But a sphere, it's the basketball I'm using, right? Yeah, so this rather dirty basketball, which is also covered in chalk dust because it's been down here for more than a week, really close to my chalkboard wall. So this side is looking rather ghostly. But this side, okay. Where's the difference between lateral and total? So I'm being kind of silly here. With the sphere, one of the things that a student has to know, because otherwise we end up getting confused, is that a sphere's lateral area is equal to its total area. With a sphere, because it doesn't have those bases top and bottom or at each end, it's all curve, it's all lateral area. So the total area is the lateral area. They're the same thing, there is no difference, which is why I'm not going to spend very much time on the sphere, because that makes us realize, wait, if there's only one type of surface area for a sphere and this is it, well, we did this last time. So we already know how to do it, which is why I'm only doing 2 examples. 4 pi r squared is going to be 4 times 3.14 times 5 squared. This is one of the fun ones to do because we can do it in our heads. Even though we have pi and we have an r that's being squared, an exponent, no, we are going to follow the order of operations, so I'm not multiplying yet. And 5 squared, of course, is 25. And 4 times 25 is 100. That's easy. We can do both of those in our heads. And 100 times 3.14 happens to also be easy. We're just moving the decimal. We're jumping the decimal 2 places to the right. So it's going to be 100 times 3.14, which is 314 square inches, area, squared unit. That was easy. How about the soccer ball? I'll write it over here. Soccer ball. The area formula is the same, and soccer ball, like the basketball, you're not going to be surprised, I hope, when I say this. The soccer ball's lateral area is equal to its total area. They're the same thing, because it's a sphere. 4 pi r squared, which is 4 times pi, that's 3.14 times, oh, what's the radius? I forgot to give the radius of the soccer ball. I'll write it here. R equals 4.5 inches. So we are doing 4.5 squared. .5 squared, well, I have to do that first before I multiply, right? So it's 4, 3.14, we'll multiply later, and then 4.5 squared is 20.25. But I'm going to get my calculator, and I'm going to double check. 4.5 squared. Yes, 20.25, and now I can multiply times 4, that's going to be 81. But I'm not going to do that last multiplication in my head. So I'm doing times 4 times 3.14, 254.34 square inches. A little bit smaller, but we expected that. If I hold up both balls at once, which I hopefully can do without dropping them and spilling my fizzy water, we can see that the lateral area and total area of this soccer ball is going to be smaller than that of the basketball because the basketball is bigger. And we knew that the radius is ½ an inch bigger on the basketball than the soccer ball. So nothing about these answers is surprising, and that means that we can go back to the cylinder, which I want to do. Ooh, 20 minutes, slightly more than 20 minutes left. I think I have time to do that painter's tape. I just feel like doing the painter's tape. maybe because I showed it to you already. So it would feel left out if we didn't find its lateral and total areas. And we even made a prediction about it, didn't we? We look at it and we feel like we can predict that the areas of the two circles are going to be greater, the two circles combined, going to be greater than the lateral area of the area of the tube. And we'll see if that's true. We'll let the formulas prove us right or prove us wrong. We need a radius, and I'm going to have to measure it to get the radius. Okay, so cylinder sphere we have covered. I'm not going to add to this list because that painter's tape is another cylinder. And the other objects that I'm going to do afterwards are also cylinders. We're just doing cylinders the rest of the way in this lesson. So therefore, I'm going to write both formulas. Area lateral is equal to 2 pi RH, and area total is equal to 2 pi RH plus 2 pi R squared. This time, instead of just plunking the answer to this in here, I'm going to show what it looks like when you have to do all of these calculations at once instead of having a shortcut. So for that reason, I'm going to find the total area first. I don't want to know the lateral area. I want to find the total area, and then I'll do the lateral area. And we won't be surprised what we get for the lateral area formula, will we? We will already have done it. We're understanding this because we understand the relationship between these two types of area and the fact that we're doing them to the same roll of painter's tape. I need the radius. It's the only, I need the height as well. I need the H, which is the height. So using this chalk dusty plastic ruler, the height of this, it's hard to see because of the dark color of the tape, making it hard for me to see the little numbers. I would say that's 1 3/8 inches. And of course, being someone who's into carpentry, I deal with measures like 1 3/8 inches very often, so I have a pretty good success at remembering the decimal versions of those. So that is the H. I'm going to plug that in. We have 2, we have pi, which is 3.14. We have R, which I'll leave room for. And the H is 1 3/8 inches, which is 1.375. Now, of course, I hope I'm not going to run out of room here. Of course, I could use the fraction. I could plunk 1 3/8 in there. We know how to deal with fractions. We can do calculations that involve fractions. But people have a tendency to switch to decimal when they're doing these formulas. Plus 2 times pi times that R that I still haven't found squared. Let's see if this will fit. I'll even write the little 2 for squared. Is that fitting? Ooh, just barely. I could have done this whole thing over this way more. There's plenty of room. But we have to have room for the teacher to stand and pose for pictures with his math, don't we? Okay, so I need the radius of this thing. This roll of painter's tape, a little easier to see the markings on the ruler with this. But I have to kind of judge to get the edge of the ruler to go right across the diameter. I don't see the midpoint marked in this, right? So I have to kind of estimate and judge it. And oh boy, is that ever 3.5 inches. Okay, the radius is 3.5. Oh wait, the diameter is 3.5 inches. When you measure directly, it's not easy to measure a radius across a round item like that. It's easier to measure the diameter. So that's why I have a space over here. It's not for the teacher to pose for pictures. It's the diameter is equal to 2 times the radius formula, and the diameter is 3.5. I know all of you could just say, oh, 3.5, that means the radius is 1.75. Why are you going through all this trouble? Because I want to show my steps, that's why. So 3.5 is equal to 2r. I do a little bit of algebra. Cancel, cancel. The radius is equal to, yes, 1.75. And that's what I want to plunk in here. And here. Whew, this painter's tape is taking longer than I thought. I want to hurry up because I have something else I want to do. But now we can simplify all this. I still have to do the exponent. So I'm being really fussy. I'm saying, no, I refuse to do any multiplication or addition. I want to follow the order of operations. So 2, 3.14, a lot of copying. 1.75, I'm writing a little bit smaller. That's messy though. 1.375 plus 2 times 3.14. Now I need 1.75 squared, and that I am not going to do in my head. 1.75 squared. Not the same as 1.75 times 2, which would have given us 3.5, but I've seen students make that mistake. Squaring, multiplying by 2, that's two different things. Slow down. 3.0625. And of course, I could have rounded that a bit, but I'm just not going to bother. I'll round later when I give the final answer. 2 times 3.14 times 1.75 times 1.375 equals 15.11125. I'm just going to write 15.1 plus 2 times 3.14 times 3.0625 equals 19.2325. And I'll just write 19.2. Yep, the lateral area is less than the combined area of the two circles, as predicted by looking at the object. Sometimes our eyes deceive us and sometimes they don't. And well, this part I did want to hurry up so I could do another example, but I guess I kind of gave myself a different shortcut in the opposite direction this time, because the lateral area is going to be the 15.1, isn't it? Okay, I'll be good, and I'll write 2 times 3.14 times 1.75 times 1.375. But then I'll write equals 15.1 because I know that's what the answer is going to be. Oh, I didn't even finish answering this. Square inches and 15.1 plus 19.2 is going to be 34.3 square inches. We did it. Lateral and total areas of the painter's tape. So many cylindrical objects in a household, really easy to find one that you can experiment with and find the lateral and total areas of. Even the can of fizzy water, I could kind of do that. The problem is that it's not really a perfect cylinder. The other ones that I've used really are cylinders. This one is mainly cylindrical in shape, and we could get a very good estimate of its lateral and total areas. But because of all these little diddly bits that allow us to have it stronger on the top, and I think this is like this on the bottom so it doesn't stick to surfaces, maybe, I'm not sure. And then there's this little tab here, so it gets complicated. But yes, in a typical household, you will find cylinders that are not complicated that you can experiment with. But this cylinder is doing a really good job of keeping me hydrated. Okay, my last example, because I actually have 3 cylinders. So I think what I'll do is I'll do all 3 of them across together with the lateral area, and then I'll erase. And if I have time, I'll do all 3 of them with total area, but I think I'll have time. And I really should, because we don't want to be pretending total area doesn't exist all of a sudden. Erase, erase, erase. What am I talking about? What objects am I talking about? I like these. These are part of my ratchet set. And all 3 of them are cylinders. They're small. They're not as easy for me to show to the camera. But what you might be able to tell is that these 2 have different radius, but they're the same height. If I move my fingers out of the way, I should be able to see. They have the same height. There. I can't even see it. The tripod is in the way and I can't see the screen very well. Different radius, same height. But these 2, so this one, okay, so there's that skinny one. I'm putting it down because I have too many things in my hands. But I kept this one. And this one, and this one, they have the same radius, but different heights. So this is the same as each of the other 2. It's got the same height as that skinny one over there, and it's got the same radius as this little short fat one over here. So I'm going to put this one in the middle. I'm going to put the formula for this one in the middle. So, I can't really, how should I do it? Should I mean, I would want to number them or something, but are the numbers meaningful? Wait, are the sizes on them? you know, these are tools. They're supposed to have sizes. Sizes that are all scratchy because the tool has been used so many times. Something is 13/16. I just can't see it well enough. So I'm going to forget about that. I will even forget about the 13/16. I'm just going to measure it. So this is going to be the one I put in the middle. It has something in common with both of the others, and we'll show that with our diagram on the chalkboard wall. So I'll start by writing a little lower so I have some room up here, the area lateral formula. But I'm going to write it 3 times. Okay, so for that middle one, let's do the measuring. The height, 2.5 inches. H equals 2.5 inches. And then its radius, I have to be careful not to accidentally use the diameter. Oh, its radius is going, the diameter looks exactly 1 inch. So the radius is 1/2 inch. There. Now, keeping this in my hand, keeping the ruler in my hand too, I'm picking up this other one. Remember the skinny one? It's got the same height. So I'm going to put the skinny one over here. The height is equal to 2.5 inches. And then what we'll do is we'll put a little double arrow thing to remind us, aha, both of these have the same height. But its radius I have to measure. 5/8 of an inch, which will be 0.625. Radius, wait, no, that's the diameter, is 0.625, so 0.3125, 0.3125 inches. Not the same. Then this one, I don't have to measure anything because I already did all the measurements. Oh wait, no, I have to measure its height. Its radius is the same as that middle one, so this time it's the radiuses that are the same. R equals 0.5 inches, but the height of this one, definitely shorter. 1 1/4, 1.25 inches. Why do I want to do this? It's me asking those what-if questions. What if you have 2 cylinders that have the same height but different radiuses? Well, we can kind of predict rather easily that since the radius of this one is smaller but the heights are the same, the lateral area of this one on the left should be smaller. So what about this? They have the same radius but different heights, but again, the height of this one over on the right is smaller than the middle one, so its lateral area should be smaller. So we're expecting the biggest lateral area to be in the middle here, and these to both be smaller than it. And we'll see how close they are to being equal to each other. I don't know. We're going to find out by doing it. Let's do the formula. We have all the information we need. 2 times pi times 0.3125 times 2.5. I have to make sure I can make all of this fit. 2 times pi times 0.5 times 2.5. Yes. Over here, 2 times pi times 0.5 times 1.25. Is this going to fit on my video window? Yes, it does. That's great. Okay, so now we have just a bunch of multiplying to do. We have 6 minutes left, which should be enough to follow this up with the total area formulas for all 3. 2 times 3.14 times 0.3125 times 2.5 equals. I'm going to round it to the nearest tenth. It's 4.9 square inches. This one, 2 times 3.14 times 0.5 times 2.5 equals 7.85. It's bigger, but we expected that, didn't we? Square inches. Last one, 2 times 3.14 times 0.5 times 1.25. 3.925 square inches. Now going the total area formulas, I'll put them below and they'll fit, but my handwriting's going to get messy. I may have to sit on my chair to do it, so I lower myself. But 4.9 is bigger than 3.925. So what we're finding out is that this tall, skinny one actually has a bigger lateral area than this short, fat one. Not hugely bigger, but it's bigger. And when we look at them and think about, does that make sense? It kind of makes sense. Yeah, I like it. Kind of makes sense. So the difference in height and the difference in radius together make a difference in area, and all sorts of stuff can happen when you vary two things like that. Let's do the total area formula, but we're going to do the shortcut. Oh, this piece of chalk is finished. Do I have another one? There's one. Is it long enough? Yes, it's long enough to finish the lesson. So the total area is going to be 4.9. I'm doing a shortcut. I'm replacing the 2 pi RH part with 4.9 because I already know that. Plus 2 pi r squared. So far my handwriting's not too messy. Area total equals 7.85 plus 2 pi r squared. And here total area equals 3.925 plus 2 pi r squared. I don't think I'm going to run out of space. Okay, I'm going to get my chair. And we have all the information we need. All we need now is the radiuses. Okay, I'm hardly fitting into this video at all anymore. It's kind of funny, eh? I look funny. Okay, 4.9 plus 2 times 3.14 times 0.3125 squared. 0.3125 squared. Hard to fit it. Equals 7.85 plus 2, 3.14. Radius is 0.5 squared. I can fit that more easily. It's a good thing this chair has wheels. Equals 3.925 plus 2 times 3.14 times, and the radius is 0.5 again, 0.5 squared. Woo! I'll grab my calculator while I'm over here because that's where it was. Okay, I have to do the squared radius first. So a lot of copying. Plus 2 times 3.14, 0.3125 squared is 0.0976. I'm going to call it 0.098. I don't want to round it too high. .5 squared, that's an easy one. It's 0.25. Why do I know that so easily? Because 0.5 is equal to a half, and half squared is a half times a half, which is a quarter. 0.25. And I'm using that again over here. 3.925 plus 2 times pi times 0.25. Now it's only the answers we have to get. I'll do the rest of the calculations all at once because I'm running out of room. So I'll do the multiplication and then add the 4.9. So I'm doing 2 times 3.14 times 0.098 equals 0.61544, but I'm adding it to 4.9 plus 4.9 equals 5.5. So this part multiplied out to only 0.6154, 0.6, very small, but remember that was the skinny one. So the area of those two circles at the ends of the really skinny cylinder, we expect it to be nice and small. And I'm putting my square inches before I can forget. 2 times 3.14 times 0.25 equals 1.57, a little bigger, but we expected that because the circles at the ends of these two are bigger. So 1.57 plus 7.85, 9.42 square inches. It's bigger than this one, but we expected that. Well, can you even see what I'm pointing at there? this one is bigger than this one, but we expected that. It doesn't matter if you see me. I can pull my head right off and just talk like this. Maybe I should do the whole lesson like this. Okay, maybe next week. Okay, and over here, oh, I already know what it's going to give me on it, but I went past that in the calculator, so I'm doing it over again. 2 times 3.14 times 0.25. Yeah, that was the 1.57 plus 3.925. 5.495. 5.495 square inches. Last thing I have to write for this lesson. Okay, now I can stand up. Maybe I should stand on the chair and then you'd see everything but my head. Okay, the things math teachers will do to help their students understand math. 5.5 inches squared, 9.42 inches squared, 5.495. Interestingly, the total areas of these two ones on the outsides, which we knew were going to be smaller than the total area of that middle one, but the total areas, the two on the outsides, ended up being very, very close to each other. In fact, with a bit of rounding, this would round it to 5.5, wouldn't it? So the lateral areas, the lateral area of this short one was quite a bit smaller than the lateral area of this tall, skinny one. But the total areas were almost the same. And that's why I like to say what if. Because I did not know this was going to happen. I didn't do all of the calculations for this ahead of time. And I've gone over my hour. So I'm going to stop talking. And someone's looking at me and saying, you are 1 minute and 44 seconds late with my supper. Doesn't stop her from wagging her tail, though. Always forgiving. Dogs are very forgiving. They put up with a lot, don't they? Don't you? Thank you very much for being here. As usual, it was a pleasure. As usual, the hour and 2 minutes raced past. Hopefully, you feel good about the concepts of lateral and total area and the concept of the cylinder, because we covered a lot of cylinders in here. Thanks again. I will see you next time.